In this presentation, we're going to talk about RC circuits, that is, circuits that have a resistor and a capacitor. We will consider two main scenarios, charging and discharging. The circuit shown here is charging. It includes a battery, and when the switch is flipped up, the battery will be in the circuit with the resistor and the capacitor, and charges will come from the battery through the resistor and end up on the capacitor, and so the capacitor will be charging. So let's talk about what happens when we close that switch. Let's talk about the three elements individually, the battery, the resistor, and the capacitor, and then talk about them when they're together. So when we have a circuit with a battery, we have charges will leave the upper side of the battery, and they will have some energy per charge, a voltage, and they must use up all that voltage and then return at the bottom of the battery, at the other side of the battery. A resistor has some difficulty to pass through, and so the charges use up some energy as they pass through it, and so the voltage in a resistor is proportional, as we know, to the current going through that resistor. And with the capacitor, we have charges landing on, in this case, the upper plate, and then some corresponding amount of positive charges leaving the bottom plate, so that the charges some charge makes its way all the way around the circuit and gets back to the battery, but it is not necessarily an individual charge that gets all the way around, but some amount of charge ends up on the capacitor and some corresponding amount of charge leaves the bottom plate of the capacitor and sort of completes the job. So in the beginning, we're imagining that this capacitor is uncharged, and so there is no voltage across it. The voltage across the capacitor is proportional to its charge. So in the beginning, there's no voltage on the capacitor, so all the voltage, all 5 volts, it gets applied to the resistor, and that gives us a certain current. But as we have this current, those charges land on the upper plate and stay there. Some other charges leave the bottom plate, but those charges from the top of the battery land on the plate and stay there, and they start then to charge the capacitor. So once the capacitor starts to be charged, some of the voltage is dropped by the capacitor, less of the voltage is dropped by the resistor, and so the current is less. So the current is going to decrease, the charge on the capacitor is going to increase, and then at some stage the push of the capacitor will equal the push of the battery, and this will come to a stop. So we have voltage across capacitor, which is proportional to charge, and voltage across a resistor, which is proportional to current. And then we must remember that current is the rate of change of charge. So in the beginning, we have a large change and a small amount of charge on the capacitor, and then as we proceed, the charge grows, but the current, the rate of change, shrinks, and so we have a function that is ever increasing, but that its slope, its rate of change, is decreasing. And the formula at the bottom that says that the charge is equal to the capacitance times the voltage, that's the net charge, that's our usual QVC, and then that gets multiplied by parentheses 1 minus the exponential function minus some time over some characteristic time called tau. The tau, or the characteristic time, in that equation is known as the time constant and happens to be equal to the resistance times the capacitance. So let's first convince you that resistance times capacitance has units of time. Make sure the units are right before we proceed any further. So we know from Ohm's law that V equals IR, but if we solve for resistance, that's voltage over current. Similarly, we have for the capacitors, we have QVC, Q equals V times C. And if we solve that for capacitance, that's charge Q over V. So if we use these, if we multiply R times C, that's multiplying by Ohm's law, the R is a voltage over current, and by the QVC rule, the capacitance is Q over V. So we have R times C has the units of voltage over current times charge over volts. One of those has volts in the numerator, the other in the denominator, so the volts cancel, and we're left with charge over current. And then we remember what current is. I is the current, is a charge per unit time. It's a rate of change of charge. So now we have Q over I becomes Q over T. So the Q's are going to cancel, and the T was in the denominator, which is the numerator. So our units are units of time. So RC has units of time. So the function we know is 1 minus an exponential, and that is shown here in this picture. And the axis we are drawing in this graph is in units of tau. So we show it at 0, at 1 tau, at 2 tau, at 3 tau. And we're going to be, and this is always the shape of the curve and always what it looks like at 1 tau, 2 tau, and 3 tau. So we're going to use this in our simulations to extract a simulational time constant and then relate it to R and C. So at a time of 1 tau, we see that we are getting 63% of our total, what we call our saturation charge. And so we will use that 0.63 number often in what we do. So here we're using our equation at two different times. One is at a time of 1 tau, and the other one is at time of infinity, the saturation charge. So if we stick in t equals tau, we get an expression that is CV, the capacitance times the voltage, times the quantity 1 minus e to the minus 1. We have tau, we have t over tau, but t is equal to tau, so it's tau over tau, which is 1. Okay. At infinity, we have CV times the quantity 1 minus the exponential to the minus infinity, so that's an exponential decay, and at infinity it decays to 0, it goes to 0 fairly rapidly, and so we have 1 minus 0, or just 1. So now if we take the ratio of these two, we have CV times the quantity 1 minus e to the minus 1, and we're dividing that by CV, so the CV's cancel, and overall we just have 1 minus the exponential to minus 1, and that's where the 63, the 0.63, the 63% comes from. There is no simple way for us to measure the charge on a capacitor, but unfortunately the voltage has a very similar relationship. In fact, just divide the charge by the capacitance and you will get the voltage. So the expression for the voltage is just Vt equals V, some saturation voltage, times the quantity 1 minus the exponential of minus t on tau. So the time constant, tau, is R times C, and it is the time when we see the charging behavior for it to get up to 63% of the saturation charge, or if we're working with voltage, the saturation voltage. And we claimed that it is R times C, and we showed that R times C has a time unit. And now let's convince ourselves further that R times C makes sense, that if the resistance is bigger, the time is bigger. If the capacitance is bigger, the time is bigger. So we are sort of putting charge onto a capacitor plate. Let's imagine filling a bathtub with water instead. So the resistance, if the resistance is large, that makes the current small. That is like having the faucet only have a little bit of water coming out at a time. So the current is the rate. So this is like having a small faucet to fill the tub. And so if you're only allowing a little bit of water out at each time, it's going to take a long time to fill up the tub. The capacitance is the size of the tub. So if you have a large tub, it's going to take a long time to fill. So time constant is R times C. The R is related to the rate at which we're charging, so it'll take a long time to charge if R is big, and C is the capacity of the thing that we're charging, so it's going to take a long time to charge if it takes a lot of charge. We are now ready to consider the other scenario, the discharging scenario. In this case, we take the battery out of the picture, but we imagine that the capacitor already has some charge on it. So that 2.2 microfarad in the picture, capacitor in the picture, we imagine has some charge on it. And then when we close the switch, those charges, positive on one side and negative on the other side, are going to take the path through the resistor to get together, and because, as we know, opposites attract. So we usually think of the battery as pushing charges around, but now there is no battery to push the charges around, so the charges are going to push themselves around. There was a push back from the capacitor, so we know the capacitor has its own push, and that push comes from the like charges on one plate repelling each other and the opposite charges on the other side of the plate being attracted. There was an insulator between the two plates preventing the positives and the negatives from getting together, but now there is a path that goes through the resistor, but there's now a path for those positives to reach those negative, and that's what's going to happen as we start to discharge. And so now we want to also talk about its time dependence. So when is this push from the capacitor large and when is it small? Well, the push, the voltage across a capacitor, is related to its charge. So when there is a big charge on the capacitor, there's going to be a big push for it to discharge. And as the charge decreases, that push is going to decrease. So the push on the charges comes from the charges themselves being on the capacitor, and then the charges are going to leave the capacitor. So as they leave the capacitor, there's going to be less push from the capacitor. So the charge is going to decrease, but the rate of charge is also going to decrease. So we're going to have a decreasing function with a decreasing slope, a decreasing rate. And the theory is just an exponential, so the charge has some initial charge Q0, and then it is times an exponential function of minus t on some characteristic time tau, and this is the same characteristic time that we saw before. So here is a picture of the discharging capacitor as a function of time, where time is measured in these tau units. And now we see that compared to where we started after 1 unit of time, one time constant, we are down to 37% of where we started. So just like the 63, this is the sort of complement of that 63, and we will use this number to get a simulational time constant when we simulate circuits.